Hello, this is Daniel. Um, I'm recording these videos as basically as a side project. I want to start recording some videos for YouTube, and I just want to basically show what I'm learning, show what I'm reviewing. In this case, I'm reviewing some topics from calculus, and basically just get to explain my thought process and hopefully help you understand some topics better and help you do better in your classes. So the first thing that we're going to do is we're going to just take a topic from the class Calculus 2, which is in the United States. And what we're going to be working on right now is going to be infinite series. So what we're going to do is we're going to work out the convergence of the interval of convergence of this infinite series over here. Okay, that's going to be the infinite series from 1 to infinity. So since we want to determine the interval of convergence, we want to basically determine for which axis this infinite series right here converges. So for this, we're going to be using the sorry, give me one sec. Okay. We're going to be working out the values of x for which this infinite series converges. So we're going to be using a pretty interesting test that's called the root test that helps us determine whether an infinite series is either convergent or divergent. And by using that test, we're basically going to be able to determine for which values of x this infinite series is going to be convergent. So we're going to be writing it down real quick. So just to remind, the root test tells us that suppose we have a limit from n to infinity of the nth root of the absolute value of a sub n, which is going to be the this part over here, the terms of the of our infinite series. Suppose that limit goes to L as n goes to infinity. We know that if L is less than 1, then this test tells us that a sub n, the infinite series, whose terms are a sub n, converges absolutely. It converges absolutely because our terms are positive. So that's because of this absolute value over here. If L is greater than 1, or the limit goes to infinity, then diverges. And if L is equal to 1, then the test doesn't tell us anything, and it basically fails. So we're basically looking out for L going either to less. In this case, we're trying to prove convergence. We want the limit to be less than 1. So here's what we're going to do. We're going to take advantage of this test. So we're going to take the limit as n goes to infinity of the nth root of the absolute value of this over here it's going to be that. So we're going to be working this out real quick. So basically, we can do the following here. We take the absolute value outside and we bring the root, the nth root inside. So we end up with this over here. So we know that this over here, we can take this out. So we end up with just the absolute value of the limit infinity of the following over here. Okay, so coming back to the video, I basically just wanted to prove, or at least show, the limit as n goes to infinity of this little function over here, the denominator of this fraction. So we have n raised to the 2 over n power, basically. So right here is a reason as to why this limit right here is going to be 1. So just to complete this, we're going to be doing the following. So we have 1/4. The limit of this over here, for as it goes to 1 over n, we know that 1 over n as n goes to infinity is going to be just 0. So this whole thing goes to 1. We're going to have 1. And we know that this over here, n to the 2 over nth, or in general, n to the 1 over nth power, it's just going to be 1. And of course, it's just 1 because we have the absolute value, and so that's fine. It stays like that. And what we end up with is this over here. All right. So now that we have this, we want to determine for which values of x this test, or this infinite series converges, this one right here. So going back to the definition of the root test, we find that if the limit is less than 1, then the infinite series is going to converge absolutely. And that's what we want, basically. We want to determine for which values of x, again, this series converges. Since this is our limit over here, we just took the limit, and this is our limit over here, we want to make this limit less than 1. Okay? That's what we want to do. So just to clean this up a little bit more, we're going to multiply both sides by 4. We end up with this right here. And since we have an absolute value over here, we're going to have that. In fact, this over here is just going to be between -4 and 4. X minus 5 is going to be between -4 and 4. That's how it is. So, and just to clean it up even more, we know that x is going to converge. We know that x is going to converge for these values right here, basically. Right? Did I do the arithmetic well? Yeah. So this is going to be the values, or the interval for which x is going to converge. So once we have this, what we want to do is we want to test the endpoints, because the endpoints are not automatically included. You know, the root test tells us for anything less than 1 or greater than 1, but not less than or equal to, or greater than or equal to. So we're going to be doing that, and let me just take out another piece of paper real quick, just to see if we need any more. And we're going to be explaining that, or we're going to be exploring that in a moment. So one sec. Okay, so we're going to be working out each endpoint just to test for either convergence or conditional convergence, just to determine the complete interval for which our original infinite series either converges or, well, converges in this case, for which values of x. So we're going to be testing the endpoints. For the first one, we're going to be doing the following. So we're going to plug in x equals 1. So we have 4. -4 to the n over n squared, -4 to the n. This simplifies to the following expression over here, so but this is just going to be equal to one to the n, but this is just going to be 1, so we can just delete it over here or erase it. It's going to be 1. It's implicit. Now, if we look closely at this expression over here, we see that we have ended up with a p-series with the p greater than 1, basically. So that tells us that this expression over here is going to converge. And since all these values right here are positive, then this converges absolutely. So for x equal to 1, series converges absolutely. Now we're going to be working on the case where x is equal to 9. So we do the same thing over here. Nice. So we further simplify this. Since we have the same powers over here, just do this. I mean, basically this is going to be 4 over -4 to the n, and 4 over -4 is going to be -1 to the n. So we end up with an alternating series over here. So we could test for conditional convergence, but we don't have to, because we have a theorem that says that if the absolute value of the terms of the series of the absolute values of the terms converge, then the actual series converges absolutely. So we're going to be doing that. We take the absolute value of this, which is just going to be, in this case, 4 over n squared. However, since we ended up with the same thing over here, we know that, again, for x equals 9, the series converges. We converge absolutely, it converges basically. So now that we have tested the endpoints, we bring back our old paper over here with all this work, and we're going to conclude that, well, basically the radius of convergence over here, we can just take 9, it's going to be right here. So we take 9 minus 1, it's going to be 8. I mean, not necessarily, really. Just r. 8 over 2 is going to be 4, so that's going to be the radius of convergence, which we saw over here. So basically, every time you end up with something like this, that's going to be your radius of convergence. And so yeah, we conclude. I can just write this just to be more formal. Conclude that the infinite series converges for the interval x between 1 and 9 inclusive. And that's going to be basically our work, and that's how you test for the convergence of an infinite series like this, for the interval of convergence or the radius of convergence or whatever. So thank you very much for watching.